All right, moving on to lifetimes. This is the part 3 of the generics chapter, or at least chapter 10. Open this up, and just to verify, we can see that. 10.3, validating references with lifetimes. Cool. One detail we didn't discuss in the references and borrowing section in chapter 4 is that every reference in Rust has a lifetime, which is the scope for which the reference is valid. Most of the time, lifetimes are implicit and inferred, just like most of the time, types are inferred. We must annotate types when multiple types are possible. In a similar way, we must annotate lifetimes when the lifetimes of references could be related in a few different ways. Rust requires us to annotate the relationships using generic lifetime parameters to ensure the actual references used at runtime will definitely be valid. The concept of lifetimes is somewhat different from tools in other programming languages, arguably making lifetimes Rust's most distinctive feature. Although we won't cover lifetimes in their entirety in this chapter, we'll discuss common ways you might encounter lifetime syntax so you can become familiar with the concept. See the advanced lifetime section in chapter 19 for more detailed information. That kind of sucks. So back to this paragraph, just go over real quick. They're saying that a lifetime is how long a variable is going to live before it gets dereferenced, right? And a lot of times this is inferred. However, there are times when we're writing code that the inferred lifetime could have multiple possibilities, and as such, we need to distinctively mark it in our code using the lifetime syntax, which in this paragraph, they told us they'll introduce that syntax to us, but they're not going to tell us anything serious about it until advanced lifetimes in chapter 19. 9 chapters away. All right, moving onward. Preventing dangling references with lifetimes. The main aim of lifetimes is to prevent dangling references, which cause a program to reference data other than the data it's intended to reference. Consider the program enlisting 10-17, which has an outer scope and an inner scope. Here's the program. We have the outer scope, which is from here to here, right? And we have this inner scope. We have let R, it just defaults to the default value, seemingly. That's just awkward. That doesn't seem like it's a compile. Let X equal 5, let R equal reference 2X, and then try to print. Let's see what the error they give us before we continue reading. So in the editor, and let R let X equal 5, R equal pointer reference to X, and now R does have a type, so that did pop up. Okay, and then we can try to print this. R and see what the value is. So let's get rid of this line here, cargo run, and the error is here. Borrowed value does not live long enough. X dropped here while still borrowed. Ah, I see what happened. Okay, so back to this example. We define R. R is fine. R did nothing wrong. However, we define X in this scope, right? And we said let X equal to 5, and then we said let R equal a reference to X. However, at the end of this scope, X no longer exists. As such, R is trying to point to something that no longer exists. See, right here? So when we try to print R, the compiler yells at us. Borrowed value does not live long enough, which makes sense. Okay. See what else they have to say? Ooh. The examples in listing 10-17, 10-18, and 10-24 Declare variables without giving them an initial value so that variable name exists in the outer scope. At first glance, this might appear to be in conflict with Rust having no null values. However, if we try to use a variable before giving it a value, we'll get a compile time error, which shows that Rust indeed does not allow null values. Yeah, that makes sense. So what they're saying here is that at initial look, this looks skeptical. This looks like it should not work because the Rust has no null values. However, the compiler is checking to see that we give it a value before we try to print it. And if we were to try to print it out without giving it a value, then we would get yelled at by the compiler. So this, at least writing code like this, though it looks awkward, by the compiler standpoint, it's fine. The outer scope declares a variable named r with no initial value, and the inner scope declares a variable named x with the initial value of 5. Inside the inner scope, we attempt to set the value of r as a reference to x. Then the inner scope ends, and we attempt to print the value in r. This code won't compile because the value that r is referring to has gone out of scope before we try to use it. Here is the error message. And here it is. X does not live long enough. That's what we saw. And then here's some examples. It was borrowed here, and then it was dropped here. Borrowed value needs to live until here, which makes sense. The variable x doesn't live long enough. The reason is that x will be out of scope when the inner scope ends on line 7. But r is still valid for the outer scope because its scope is larger. We say that it lives longer. If Rust allowed this code to work, r would be referencing memory that was deallocated when x went out of scope, and anything we try to do with r wouldn't work correctly. So how does Rust determine that this code is invalid? It uses a borrow checker. The borrow checker. The Rust compiler has a borrow checker that compares scopes to determine whether all borrows are valid. Listing 1018 shows the same code as listing 1017, but with annotations showing the lifetimes of the variables. So I guess call it prime of A, prime of B, no, just joking around. So they have this R thing, right? And it says that R lives from here to here. That's the lifetime of it. And we have the lifetime of this X, which is from here to here. Oh, here to here, to be explicit. And as you can see, X does not live long enough to be used again in this scope, or at least at this line. And since R is trying to reference X, we get an error. Here we annotated the lifetime of R with prime A, apostrophe A, but prime A, and the lifetime of X with prime B. As you can see, the inner prime B block is much smaller than the outer prime A lifetime block. At compile time, Rust compares the size of the two lifetimes and sees that R has a lifetime of prime A, but that it refers to a memory with a lifetime of prime B. The program is rejected because prime B is shorter than prime A. The subject of the reference doesn't live as long as the reference. Listing 10-19 fixes the code so it doesn't have a dangling reference and compiles without any errors. And what they did was put X and R into the same scope. So now they have the same lifetime. More or less, they die at the same time. They don't start at the same time though. So X starts from here, prime of B, and R starts from here, prime of A. But they both die here. Here, X has a lifetime of prime B, which in this case is larger than prime A. This means R can reference X because Rust knows that the reference in R will always be valid while X is valid. Now that you know where the lifetimes of references are and how Rust analyzes lifetimes to ensure references will always be valid, let's explore generic lifetime of parameters and return values in the context of functions. Okay, generic lifetimes in functions. Okay, we want to figure out how to do lifetimes in functions. Let's write a function that returns the longer of two string slices. This function will take two string slices and return a string slice. After we've implemented the longest function, the code in listing 10-20 should print the longest string is, and then the string A, B, C, D. And then here's the program, file name, source, main file. So let's write that out. So we have let string1 equal string from A, B, C, D. Okay. Let string2 equal, oh, that's char, X, Y, Z. Let result equal, oh, they have a function called longest string. That's what they were mentioning up there, but they don't write the function here. Can we continue? Oh, wait. The function's down there. I see it. Cool. So let's continue. Longest, and we pass in string1 as string and string2. Then we print them. The longest string is result. Okay, so we have the code from the main here. However, we do not have code for this function, longest. Note that we want the function to take string slices, which are references, because we don't want the longest function to take ownership of its parameters. We want to allow the function to accept slices of a string, the type stored in the variable string1, as well as string literals, which is what variable string2 contains. So basically what they're saying here is they're stating the requirements for this longest function. And the only real requirement seemingly is that it does not take ownership of the strings it's comparing. As such, we need to pass in references to strings. So here, this is a string reference. As you can see here, has that and symbol, so it's a reference to a string. Here, this is a capital S string, which if we pass that in directly will take ownership, or ownership will need to be passed, because this is on the heap. But seemingly we can do the string1 dot as string, and that should make it a that should make it a and string lowercase s, so it's a reference. Refer to the string slices as parameter section in chapter 4 for more discussion about why the parameters we used in listing 10-20 are the ones we want. Yep, okay. If we try to implement the longest function as shown in listing 10-21, it won't compile. And let's see it in action. Function, I like my functions above main. Put it here. Function longest. And we have two parameters, x, which we said should be string, y, which we said to be string. Both of these are references to strings. And then we wanted to return one of these references. And then if x dot length is greater than y dot length, x. Hold on, come down here. Else y. Okay, that makes sense actually. We pass in x, we pass in y. We check their length against each other, and we have an if else that is guaranteed to return something. And this is not going to compile. At least that's what they told us. Let's just find out why. Ooh. Huh. Missing lifetime specifier. That's very specific, but not very helpful. Help. This function return type contained a borrowed value. but the signature does not say whether it is borrowed from X or Y. I see. Okay. I guess that makes sense. Let's see what they say here. So they get the same error, missing lifetime specifier, expected lifetime specifier, and pretty much in the help they say the ambiguity seemingly is they don't know if this is X or Y. And as such, that's multiple possibilities. You can't infer which one is going to be. The help text reveals that the return type needs a generic lifetime parameter on it because Rust can't tell whether the reference being returned refers to X or Y. Actually, we don't either, because the if block in the body of this function returns a reference to X and the else block returns a reference to Y. Okay, restating the issue. Got it. When we're defining this function, we don't know the concrete values that will be passed into this function, so we don't know whether the if case or the else case will be executed. We also don't know the concrete lifetimes of the references that will be passed in, so we can't look at the scopes as we did in listing 10-18 and 10-19 to determine whether the reference we return will always be valid. The borrow checker can't determine this either because it doesn't know how the lifetimes of X and Y relate to the lifetime of the return value. To fix this error, we will add generic lifetime parameters that define the relationship between the references so that the borrow checker can perform its analysis. Alright, so this makes sense to me, seemingly. Let me try to rehash it. So what they're saying here is, one, in terms of this longest function, we have this return value, which is going to be associated with either X or Y. But the compiler doesn't know, and we don't either because of the way it's written. And because of what we want, we really don't know what's going to be returned, X or Y. However, the bigger issue, and more important one, is that X is a reference, Y is a reference. We see here that X is a reference to string 1, Y is a reference to string 2. Both of these have lifetimes, but with reference to longest, longest has no idea how long these things are going to live for. And because of the way it's written, it's in a different functional entirely. We can't do what we did previously in the other examples, which is just look at the scope and figure out how long things are going to live for. Because we can't determine how long these items are going to live for, and the borrow checker can't either, Rust is requiring that we add a lifetime parameter to the function, or at least function signature. That's what I believe they want us to do. Let's continue on and see what happens. Oh, one thing I should mention is that adding this lifetime parameter or syntax should help the borrow checker understand how long these references will live for, and guarantee that these references will live at least to the end of this scope, so it can return something and still be used. At least that's my understanding. Let's see. Lifetime annotation syntax. Lifetime annotations don't change how long any of the references live, just as functions can accept any type when the signature specifies a generic parameter. Functions can accept references with any lifetime by specifying a generic lifetime parameter. Lifetime annotations describe the relationships of the lifetimes of multiple references to each other without affecting the lifetimes. That was really wordy and confusing, but seemingly what they're saying here is that regardless of what we write down, this is not going to affect how long any of these variables will live for. Which is confusing because we need to tell the compiler that these things will live for a certain amount of time in order to continue writing this function. Hold on, let's continue. Lifetime annotations have a slightly unusual syntax. The names of lifetime parameters must start with an apostrophe and are usually all lowercase and very short, like generic types. Most people use the name apostrophe A. We place lifetime parameter annotations after the ampersand of a reference, using a space to separate the annotation from the reference's type. Before we continue on, this is an example. Here's a reference. Here's a reference with an explicit lifetime, and here's a reference, a mutable reference with an explicit lifetime. So what they said here is that to put a generic lifetime parameter, after this, the ampersand, we just put apostrophe and a short letter or word, depending on how we feel like writing it. And if it's mutable, we still put mutable, but that comes after the lifetime annotation or syntax. Here are some examples. A reference to the I32 without a lifetime parameter, first one. A reference to I32 that has a lifetime parameter named apostrophe A, second one. And a mutable reference to an I32 that also has a lifetime parameter. Okay, mutable reference, yeah. One lifetime annotation by itself doesn't have much meaning because annotations are meant to tell Rust how generic lifetime parameters of multiple references relate to each other. For example, let's say we have a function with the parameter first that is a reference to an I32 with a lifetime of apostrophe A. The function also has another parameter named second that's another reference to an I32 that also has a lifetime of apostrophe A. The lifetime annotations indicate that the references first and second must both live as long as that generic lifetime. I'm starting to understand. So kind of similar to what they set up here, but here they have an actual example, which is very helpful, is our lifetime parameters, the ones that we write, do not change the lifetime of the variables themselves. However, at least according to this paragraph, they tell us how long these variables' lifetimes are related to each other. And in this example where they use first and second, they gave it the same lifetime parameter, which means that both first and second are going to live at least the same amount of life, or they're going to die a relatively the same amount of time. Thus, it's okay to return first or second in this scenario. So let me just test that out real quick before we move on. Apostrophe A, right? Space. They put it in the function. Did they give us an example of that yet? Undeclared lifetime. I don't. Apostrophe A. Space. Apostrophe A space. That seems wrong. Okay, let's keep going and see what happens, because that doesn't seem right at all. Ah, here is the function signature for it. I was close. They have this thing here. Let me put this here before I read it. See if that works. Apostrophe A, and all the red underlines went away. And let's run this function again, and we have the answer. The longest string is ABCD. Cool. So let's get back to this. Lifetime annotations in function signatures. Now let's examine lifetime annotations in the context of the largest function. As with generic type parameters, we need to declare generic lifetime parameters inside angle brackets between the function name and the parameter list. The constraint we want to express in the signature is that all the references in the parameters and the return value must have the same lifetime. We'll name a lifetime apostrophe A and then add it to each reference as shown in listing 10-22. Alright, so we already did the adding portion. Here's the angle brackets for the syntax of generic lifetimes. We have to use apostrophe A. I guess that denotes this is going to be a lifetime instead of a generic type parameter. And then we add apostrophe A to each of the variables that can possibly be returned as this thing to ensure that this function knows these items are going to live at least as long as needed for this function to return something. Seemingly, that's what I'm getting from this. This code should compile and produce the result we want when we use it with the main function in listing 1022. The function signature tells Rust that for some lifetime prime of A, or apostrophe A, the function takes two parameters, both of which are string slices and live at least as long as the lifetime apostrophe A. The function signature also tells Rust that the string slice returned from the function will live at least as long as the lifetime apostrophe A. These constraints are what we want Rust to enforce. Remember, when we specify the lifetime parameter in this function signature, we're not changing the lifetime of any values passed in or returned. Rather, we're specifying that the borrow checker should reject any values that don't adhere to these constraints. Note that the longest function doesn't need to know exactly how long x and y will live, only that some scope can be substituted for a that will satisfy the signature. Okay? So seemingly what they're saying here, I say seemingly because I'm a little shaky, is that we already know that we don't care how long x and y are going to live for, because we can't change that. All we're doing now by specifying this apostrophe a, this lifetime parameter, is putting a new constraint on the function, saying that anything that's going to be passed in is going to live as long as this lifetime specifier a. And as long as the things that are passed in satisfy this constraint, then our code will compile. So for example, seemingly, based on what they said here, if x no longer existed by the time, if this string or this reference no longer existed by the time we tried to use it in longest, then this code wouldn't compile. And I think we can test that out. So if we wanted to test that out, we have to do something similar to what we did in the earlier example. We'll declare string2, but we won't give it anything, right? And then in an inner scope, we can say, I don't know, let string3 equal something else. String3 equal, what was it, XYZ? Let's not make it XYZ. We can still make it XYZ, but let's not make it a reference. Let's make it something from the heap. From XYZ, right? And then we can say string2 is equal to the reference to string3. That's a reference to string itself. So let's say string3 dot as string, and yeah, now we got the type that we want. And seemingly this will not compile because string2 at the end of this scope, well, hold on, this should not compile because string3 only exists within this inner scope. And even though we're pointing string2 to the string3 reference, since string3 is going to be deallocated, string2 should point to nothing or null or empty space in memory. And that says this should not compile. And this is the error that we get. String3 does not live long enough. The reason, I believe the reason why it's saying it does not live long enough is because in the longest function, we gave the constraint of this lifetime specifier that said everything that comes in here has to live as long as a. That makes sense. String3 was dropped there while still being borrowed, and borrowed last used there. Yeah, string3 does not live long enough. Okay, that makes sense. When annotating lifetimes and functions, the annotation goes in the function signature, not in the function body. Rust can analyze the code within the function without any help. However, when a function has references to or from code outside that function, it becomes almost impossible for Rust to figure out the lifetimes of the parameters or return values on its own. The lifetimes must be different each time the function is called. This is why we need to annotate lifetimes manually. Alright, so this paragraph is basically explaining the situation in which why we have to specify the lifetime parameter, so using the syntax, the lifetime thing. And the reason is, this is a function. This function and the compiler, the Rust compiler, can analyze everything inside of the function, but it cannot analyze things outside of this function scope, or this function itself. And given that this function has the variables coming from the outside, which are all references, the compiler cannot tell if these references are going to live long enough for them to be used adequately or as expected in this function. And so we put an extra constraint, and that constraint is this lifetime specifier, in this case A, apostrophe A, which states that these items that are passed in to be represented as X and Y are going to live as long as, well, this return value. And anything that fails the constraint is not going to compile, which we already did an example of. Moving on. When we pass concrete references to longest, the concrete lifetime that is substituted for apostrophe A is the part of the scope of X that overlaps with the scope of Y. In other words, the generic lifetime apostrophe A will get the concrete lifetime that is equal to the smaller of the lifetimes of X and Y. Because we've annotated the return reference with the same lifetime parameter apostrophe A, the return reference will also be valid for the length of the smaller of the lifetimes of X and Y. Okay, so what they're saying here is they're just elaborating on the constraint that is the lifetime parameter. And so we can paint an example, right? The lifetime of X may be equal to, less than, or greater than the lifetime of Y. So when we have X and Y, they don't have to have the same lifetime. But A is referencing or is relating one lifetime to the other. Because it's relating the two lifetimes, and we need this function to be valid, it seemingly makes sense that A should be equal to the shorter of the two lifetimes. Mainly because if it was equal to the longest of the two lifetimes, there's no guarantee that the shorter lifetime would still be valid. Actually, by definition, the shorter lifetime should probably not be valid. But that's beside the point. The point is that A, in terms of a concrete lifetime, if you had to think about it, is going to be equivalent to the shortest lifetime of the values it's associated with. Let's look at how the lifetime annotation restrict the longest function by passing in references that have different concrete lifetimes. Listing 10-23 is a straightforward example. Okay, so this is slightly different from our example. Here we have the first string, which is in the outer scope, and we have the inner scope, which includes the second string, and the result, and the return value. So the string 1 should have a longer lifetime than string 2. But that shouldn't matter because this is still work. So let's try that out. So let's get rid of this. Oh, didn't mean to move that over. Yeah, let me just my keyboard. That stays there. Make you string 2. Move this line. Move this line to here. And move the print there to move the print there as well. So this looks about the same. We have the outer scope, we have the inner scope, and this runs. Yes. So in terms of this concrete example, this outer scope, which is going to be associated with our X, has a longer lifetime than Y, which is string 2. And this A should be equal to, in terms of lifetimes, the shorter lifetime, which is Y. In this example, string 1 is valid until the end of the outer scope. String 2 is valid until the end of the inner scope. And result references something that is valid until the end of the inner scope. Run this code and you see that the borrow checker approves of this code. It compiles and prints. Oh, they changed their string. I didn't change mine. Meh. Next, let's try an example that shows that the lifetime of the reference and result must be the smaller lifetime of the two arguments. We'll move the declaration of the result variable outside the inner scope, but leave the assignment of the value to the result variable inside the scope with string 2. Then we'll move the print line that uses result outside the inner scope after the inner scope has ended. Okay, and they're saying that this code will not compile. So basically what they're saying is that we're going to move the result variable to out here, result, not declare it, give it a value in the inner scope with string 2, and then move the print line, Control X, outside of the inner scope. Paste. And for clarity's sake, we have some things that are different than them. Let's change that. Long string is long. And this is not a string reference anymore. This is string from XYZ. And that means this has to be changed to that, string to that as string to make it a reference. So that satisfies the inputs. Oh, double quotes. XYZ. And they want us to have result here. So first, let's make sure this does not compile. Cool, cool, I was scared. This did not compile. And it says that the borrowed value does not live long enough, and it's pointing to string 2. Okay, so that makes sense. So what they're saying here is that because of our lifetime parameters, we know that this result type has a lifetime that's equivalent, or this result value has a lifetime that is equivalent to the shortest lifetime of the passed in parameters that have the same lifetime parameter. So X and Y both being passed in, they have different lifetimes. X is associated with string 1, which is in the outer scope. It's fine. It exists all the way down to here. But Y is associated with string 2, which exists in this scope, which gets deallocated at this point. Because string 2 gets deallocated at this point, and string 2 has the possibility of being our result, this code does not compile, and it yells at us that string 2 does not live long enough. That makes sense. When I was first going through this, I made a mistake in writing it, and what I did was, instead of this being string from, I made this a string literal. And if you remember, the difference between a string literal and a string from is one is on the heap and one is not on the heap. But there's another difference. Print this out. Ooh, gotta take this away, because I can just pass it in directly. So the other difference, note that this ran and it went through without erroring. The other difference that is important is that string literals are hard-coded into our binary, and thus they are accessible throughout your entire program. This chapter covers it at the very, very end. This is my second time going through this recording. My camera froze. Anyway, yeah. So string literals are hard-coded into your binary, and thus you have access to them for the entirety of your program. And they have a lifetime of static. Just something to note. It gets covered a little bit. This gets covered in more detail a little bit later. But for clarity's sake, let me just go back to what they had. String from XYZ dot string, and we get that error again. Cool. So when we try to compile this code, we get this error, and it says what we expected. string 2 does not live long enough, which is what we have here. The error shows that for result to be valid for the print line statement, string 2 would need to be valid until the end of the outer scope. Rust knows this because we annotated the lifetimes of the function parameters and return values using the same lifetime parameter '(a). As humans, we can look at this code and see that string 1 is longer than string 2, and therefore result will contain a reference to string 1. Because string 1 has not gone out of scope yet, a reference to string 1 will still be valid for this print line. Yeah. However, the compiler can't see that the reference is valid in this case. We've told Rust that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes of the references passed in. Therefore, the borrow checker disallows the code in listing 10-24 as possibly having invalid references. So what they're saying here, let me move this over, is that when we look at this, we can see that string 1 is clearly longer than string 2, and that our longest is definitely going to return a reference to string 1. However, because of our annotations and the way it's defined, we said that the reference return is going to have a lifetime equivalent to the lifetime of the smaller parameter passed in that shares the lifetime parameter of a, and that is y. Because that is the case, when result is returned, we know that result is going to have the lifetime that is equivalent to string 2, which was our y, which is our short of the lifetimes. And as such, the compiler is going to say, no, this code is not going to work. Try designing more experiments that vary the values and lifetimes of the references passed into the longest function and how the return reference is used. Make hypotheses about whether or not your experiment will pass the borrow checker before you compile, then check to see if you're right.